Yeah. So let's get started. The idea today is to go over this book, or in every Tuesday stream in the book day, Parallel and Concurrent Programming in Haskell. This is the book. I can share in the chat the link. It's a great book so far. The parts that I've been reading, I really like it. The author is Simon Mavro, who also worked on GHC and worked on the concurrent and parallel runtime parts of the runtime. Then he built or worked on the parallel garbage collector as well, so I guess we can say that he knows what he's talking about. That's probably even an understatement. Yeah, and he mentions that during his classes that he was presenting, he came up with the idea to write the book based on some of the content of the classes, and then it turns out that was just more work. It's not a small book. Yeah, pages, around 300 pages with a lot of exercises. The exercises are here, but I suggest you to get the book as well. And yeah, so the first section, it can be read online, so okay, so it starts with some small introduction on what is parallelism and concurrency, and then the tools that we're going to be using. And then there was anything in the book that was worth sharing. Okay, so in the introduction, well, it mentions the distinction between what is parallelism and what is concurrency, and we can say that basically parallelism is running things in parallel, different processors, and it's something that started to be more relevant probably in the last 2 decades, when processors stopped getting faster and started adding more cores. And concurrency is more about how we structure programs that have to do several things and concurrently. So it depends. If you have several cores, they can be done in parallel, but that's necessarily the case. Like you can have only one core and still write concurrent programs. And then it makes also some comments about deterministic and not deterministic programs. So if they are deterministic, if a program is deterministic, you can run them in parallel or sequentially with the same results, and that's when you get a lot of benefits of doing like basically pure programs, like, I don't know, calculating some mathematical computations or any processing that takes a long time. Then you can run it in parallel, and if it's deterministic, the Haskell runtime can guarantee that you can run it sequentially for debugging, but then when you run it in production in parallel, when you enable multi-cores, it will produce the same results. And then if it's not deterministic, you don't have the same guarantees, and that's it doesn't make like a straight connection between like deterministic then are fit for parallelism and non-deterministic for concurrency, but it's kind of what it mentions. And it also in the introduction goes to it also goes to mentioning that basically you need different tools for different type of problems, and there are a lot of types of problems, concurrency and parallelism. So you have again the deterministic programs, but also you have real world programs, like not real world because calculations could be also real world, but like a server or something like that, and it's not doing only deterministic and pure stuff, and it's fit for concurrency. Yeah, so that's like a very brief and short introduction. And then it also mentions that basically the book is split in two parts. One is about parallel Haskell and the other is one about concurrent Haskell. And basically we'll start with the first one, which is so the chapter 2, which is the first section, which is parallel Haskell, and then we'll take a look now at the basics of parallelism, the evaluation monad. So with this and well, in the chapter 2. I think we can write code here. Okay. Run that, should let it runs. Yes. And let's take a look at the exercises. So there were not like chapter exercises to solve at the beginning. So I'm just gonna basically do the exercises that the book is mentioning. One interesting thing about Haskell that is different from other languages, and it's also the tricky part for concurrency is and parallelism, is the lazy evaluation. So one of the first things that the book goes to mention is basically weak head normal form and versus normal form. Yeah, so let's take a look at that in the repo. That's better. So if we have x, which is 1 plus 2 int, first sure we don't get any weird defaults. So we check. Normally in any other languages this will mean that x is 3 because they are evaluated, but if we check with print if x was evaluated, we get that it wasn't yet. This underscore means it was not evaluated, and then we evaluated now with this, and now we know that the x is a 3, Hello to everybody that joined. See what you're doing. So we are going through the second chapter, which is the first chapter of the parallelism part of the book, and it starts talking about the implications of lazy evaluation. Yeah, so let's print x. Now, so basically it explains that the underscore means this is kind of like it is a thing, x that points to the plus 1 plus 2. So basically, yeah, it's like a pointer to something in memory that gets past the lazy evaluation. And then we can define, let's define x again. Define plus 2. So again, now x is not evaluated, and we can also find y, which is x plus 2, and y is not evaluated either. And now both, yeah, so basically both x and y are things, and they point to the objects in memory that represents the calculation that will happen. And yeah, there is no way to inspect the tanks. At least that's what the book mentioned. So if we compute the value of y, we get that both now are evaluated, right? Let's define them again. Make them x, y. So now again, not evaluated. And now, so there is a way to force the evaluation. So type of stack, yeah, it takes an A and then a B and returns the B, but also evaluates that A. So if we do stack of y, now we see that these, both of them, x and y, were evaluated because y was evaluated. Yeah, so this has a lot of implications in the way you run parallel programs as well. I mentioned that this first section is talking about Whitehead normal form. So what that means, hey, hello Vlad, how you doing? How was the stream today? Really don't remember if I was able to watch it or not. I think I watched yesterday. So Whitehead normal form. So it means that it evaluates like the first level of the structure. So let me check the example again. But okay, so let's define our x again, and so we see it's not evaluated, and then we define yes, teaching Denisa an important lesson. Never trust programming estimations. Yes, that why would you trust them? So if we have a tuple with x and x in our y, so now y is why is it like that? I thought it would be unevaluated. So the yeah, I'm forgetting what I read in the book. So here we see that if we evaluate x, yeah, I guess, but I thought that it wouldn't be in with head number form. So I thought it will be y equals underscore until you evaluate, you do the sec. Anyway, so now if we check, now we see that the trees are there, but before the elements inside were not evaluated yet. Okay, so let's make the same thing again. X, Y, use speed. Yeah, so now we have this unevaluated. And now if we do, happens if we do sec of c. Yeah, so that's what I was getting confused with. So this is still just evaluating like the first level, which is what yeah, let's try that first c. So that evaluates the first element, and it's probably because x is, it's the same x. So let's try again with 1 plus 2, then c is x, or let's say y, which is x plus 1 beginning, and then c will be x, y. So C, it's, yeah, the head only, and if we do first, it only evaluated the first one, because now the y is still unevaluated, which is the second element of the tuple. Yep. Okay, so now for data tuple, and we define it as, just define x again. Cool. So c is of x plus 1, I think. Yes, so basically swap, what swap does is takes the tuple with a and b and then returns the tuple of b and a. And if you check the this, then yeah, it's still only evaluating the head. So the components of the pair are not evaluated yet. And yes, if we evaluate x, then yes. So what happened here? We had the x in the first, and then in the second we have a thing with the operation x plus 1. But we swapped them, so the x went to the second element and the x plus 1 went to the first one. But swap is not evaluating it either, so it was not yet calculated. So if we evaluate x, we see that now the second element is evaluated, but still the first one is not. Yeah. So now the other thing that book goes to is to take a look at the list. So the map is basically building a lazy list. You can take a look at the station. This, by the way, is one of the things I like the most about Haskell. Like, you search something in Google and you quickly get into the source. Yes. So where is map? Here. Okay, so if the list is empty, it returns an empty list. Otherwise, the pattern match on the head of the list and the rest, and returns the map, the function applied to the first element, and the list with the rest of the map, the rest of the list mapped as well. And this is also a lazy list. So until you use it, it won't be evaluated, and that's why you can do things like map over an infinite list. Okay, so maybe now it's worth make the drawing. Okay, so what the author mentions is that basically we have like the cons operator, this one. Yeah, that's the map. Each of these points to a new one. Where we have here we have the F, F and the X. Here we have 3 boxes actually. So so these are tanks that are built. Right. In the second case. Now let's go back to the repo. Say we have X's now, which is as 1 from of the list of 1 to 10. So X's is not evaluated, and then for example if we do the length of X's, it's 10, and if we check now we see that what was evaluated was only basically the structure of the list, which is also called the spine, but the elements of the list are not evaluated yet, because the length only goes through the structure, but it doesn't evaluate the elements. And yeah, I should have done it. Now print back evaluated and use tag here of the list. So this is an interesting one. So it gets evaluated the head and the rest, because this is basically the structure is evaluated to. So then we can do the length, then the whole spine of the list is evaluated, and we do sum of x's. Now all of them. Okay, so that's basically how, in brief and probably with omitting quite some from the book, but this is how Haskell code is evaluated. Anything until now, like question or anything that would be nice to review? Chat. Okay, so that's basically the part about quick get normal form. And now go to the eval mode. So eval mode. So it's a monad that makes it easier to define parallel strategy. It's basically an identity monad. It lets you evaluate things in parallel or sequentially, depending what your strategy is for evaluation. And where was I? Okay, so there should be a run eval around here. Yes, so it takes an eval monad and returns a, and like you see that this is all pure, right? So, and then there is a var, which is a strategy and runs things in parallel, and rsec runs things sequentially. But it evaluates to weak head normal fold, not to the full thing. Okay. Then there is this one, R0 with performance node evaluation. I think they are explained later in the book. Yeah. So okay, but start to get interesting. Import for parallel. example is okay. So we have r x and here, then we return a. So this language are very simple, but okay, so this is just I think this should be just tuple with the same type in both. But what's happening here? So it runs the val, so this is something in the val monad, and what it does is first get something parallel, then the next one in parallel does both. So this would look something. So we have the return, evaluation of each of both states, like where f x the a f y produce the b, and return. Here, and this is called r bar. Yes. Okay. And that's because, and yeah, this is when the return here happens, because both are evaluated in parallel. So r 2, got it. And then we have rsec. So, linter doesn't like it. And yeah, so that one is sequentially. So what happens here, it's copy this, happens is that the line with the return moves here. Because this is evaluated in parallel and this is evaluated sequentially. So it will wait for this one to finish evaluation, and then it will return. And then, yeah, if we really want to wait for both, we can do something like this, or we do this, right? Yeah. So now we have another one. Hello to the people in chat, supposed to join. Yeah. Tech. So now I guess you can guess it, but this moves line here because now we're waiting. First we wait for sorry, this is in parallel, then we do this sequentially, wait for this one to finish, and then we wait for this one. They use RSec, yes. Now the problem here is what happens if this is actually okay. So the problem with these ones is that we don't know which one will basically finish first. It might also look like that. Okay. Yep. Then there is another variant. But it did add RSec, so this is, and then do this, and I think, yeah, these achieve same results. And the first one, so it's kind of like you can choose whichever you want. And was there any note of this? And I should point out that basically, yeah, because this is just doing the evaluation of where we are passing, they shouldn't be evaluated yet. So if you provide something that is already in weak-head normal form, the eval monad is not going to do anything. Okay, so let's try to run both. Okay, we're all related to Unite. So we have right. So if we run bib of 36, control parallel strategy library parallel. Okay, Let's x, y, if, and f is just x. What is wrong with compiling? Yeah, so you see it takes a little bit, and we should add as part is I guess we should be like output. Should be showing the time.
You must be missing me so bad. When you left, you said that I don't deserve you, but I can see that you don't wanna lose what we had. Oh, you're the one that I need. Let's just take it slow and just breathe. Loving someone
Okay, let's use time for now. Took 9 seconds the user, and then so what is the example? So let's try this. Ah, okay, I see why it's because this is copy. Okay, so the first example that runs both in parallel, it takes 1.3 seconds. But let's try the second example, which runs one in parallel and the other sequential. And yeah, so it takes the same amount of time, but it looks okay. So basically in the second one we are, so in the first one we are here, time seen that the first time is this one, it returns instantly, and then evaluates 2 of them, then returns the time, yeah, the final time. Well, the second returns after some time, then evaluates 2 and then prints the other time. And the fourth, the third one does, so the second one was this one. It returns as soon as the first evaluate and then continues. And the third one is this, so it evaluates both and then returns. And the fourth is just similar version. I wonder why one is faster than the other. It's probably caching. Hello, Ancient Instant. That's a cool name. How are you doing? Thanks for joining. We are all good. Sorry if I missed your name from like the free Slack or something. I'm saying this every stream, but people join and I don't. Either they have different usernames or. So we are going through the parallel and concurrent. Thank you. So we are going through the parallel and concurrent programming book, just the beginning, checking how the eval monad works. Okay, so this one was, it's the part rsec. It's, where is Haskell used? Oh, okay, that's a good question. So Haskell, it's a general purpose programming language, so you can use it for any like server side stuff. Some people use it even for client side because it compiles JavaScript as well, although that story might be not the best, I don't know. But since it's a functional programming language and it's lazy, it's used for data processing, writing compilers, parsing data, ESLs, embedded languages. For example, the author of the book works in Facebook, and they use it for spam. Yes, they use it for a spam filter. It's a server they wrote a spam filter. It's actually by Simon Marlowe, which is the author of the book. But maybe people in chat can also share about it. It's also used for research of type systems, functional programming. Yeah, I would like to say the same, but unfortunately cannot. Okay, so that was basically how to use the basics of evaluation parallel and sequentially.